I'm going to start us a little bit early, just because the speakers that we have today, they've got a full 30 minutes. If you looked at your session, if you looked at what's going on, this session is all day. We have got 7 speakers who are going to talk on things related to precision IPM, advanced technology, whatever. You see the title up there. You are in the right session if that's your interest. But we're going to start a little early to kick this off. And the one thing that we do have at the end is our Q&A session. That will be the time for folks to ask questions. So I know you guys have a lot of things that you want to ask these people, and that's entirely possible, but it's going to be at the end of the day. So that's your kind of hook to stay around. Anyway, so my name is Steve Young. I'm the director of the Northeastern IPM Center. My colleague Jeff Bradshaw at the University of Nebraska-Lincoln and Ian McCrae, who's at the University of Minnesota, got together, I think it was last year and even before that, talking about technology applications to our different disciplines. Jeff's an entomologist. I'm a weed scientist. Ian is a entomologist too. So we got together, we talked about this, and we thought, you know, it would be really good to kind of bring in people that are working in this field, both the biologists and the engineers and the computer scientists, the regulatory people, bring them all together to talk about this topic of IPM and how does technology apply to it. So we've got very knowledgeable folks that are going to talk today. I think you're going to enjoy hearing from them, and definitely, as I said, ask these people questions either at our Q&A session or even during the break. One thing I want to let everyone know is we are recording this. We're not streaming it live, we are recording it, and we plan to post this to our website after the symposium. We want to make this available to a wider audience that I think would be interested in hearing about this. So I would like to introduce our first speaker. This is Dr. Ken Giles from the University of California, Davis. And Ken is an engineer and a biological systems engineer. And he's been working in the field of robotics for quite a while. And so he's going to talk to us today about some of the work that he's doing. And we'll hear from Ken. So Ken, come on up.
All right, thanks. Everybody hear me okay with this? Great. First off, thank you very much, Steve, for the chance to come and chat with an audience that I don't always see. I want to acknowledge all the folks that contributed to this. Dave Slaughter, my colleague, ag engineer, and also Steve Fenimore and Richard Smith down in Salinas with some of the vegetable work. A lot of what I'll be talking about today is about effectively delivering a payload. We used to call it spraying. Now it's a bigger set of tasks that we have. We are delivering some agent. So we tend to work a lot on the actual implementation of pest control decision, be it typically spraying or delivering some agent. And that's what I'll be talking about today as we've automated that, as we've brought in other technologies. I also want to emphasize today, you'll see a lot of longitudinal information in that it takes a while to get technology to the field. So some of the things you'll see were in development for many years, and in many cases recently have become commercialized. The other thing I want us to keep in mind, and this was something I learned very acutely as an engineer working in the field, is when we go out and we talk about pest control operations, we really have 3 objectives. Often we're focused on one, but those 3 are first, the efficacy of our application, and secondly, off-site protection of non-targets, and then finally, and this is often overlooked, the productivity. You go talk to people that actually implement IPM, and they say, I've got to get acres per hour, I've got to get hectares per day. I've got to be productive. And we can't come up with technologies that really have a negative impact on any of these objectives when we go out and spray. It can be incredibly efficacious, but if it takes forever to do, it simply won't get used. So we have to keep these in mind. Certainly efficacy, for many years that was the focus, even something as simple as looking at droplet size. A lot of focus was on improving efficacy as a way of reducing application rates. So certainly that is, and probably for most people in the audience, efficacy is the primary concern. Now, if I was talking to a regulatory group, their concern would be in off-site protection. Spray drift. You know, there's an entire industry out there devoted to spray drift. The prevention of spray drift, the litigation after spray drift, the selling of products for mitigating drift. But it is something that we have to be aware of, and also not just spray drift, but ground deposit and worker exposure. So yes, we can improve efficacy of our application, but not at the expense of off-target effects. And similarly, productivity, I think, is the most, especially in the research community, the most overlooked aspect of implementing IPM in pest control operations. And this is everything from reducing our rates so that we have less payload demand on our vehicles, higher ground speeds, higher work rates, wider weather windows, everything that really allows that applicator or that implementer of our decision to get their job done. So in engineering decisions, efficacy, reducing the non-target effects, and also productivity, any successful technology, and I'll show you some examples today, any successful technology has got to improve one of these and at least be neutral on the other two, not make it worse. We haven't seen any technologies that are successful without some recognition of these three factors. We also have, and a lot of all my examples will be from the West, primarily in specialty crops, and we have tremendous diversity in our agriculture. We are always, everywhere we grow, we're in proximity to a sensitive area or to a non-target crop. And that's why such things as buffer zones for spraying are really challenging for us. If you apply a buffer zone to any of these crops, due to, say, a waterway, you effectively reduce the farmable land that we have significantly. So we have these constraints, these three constraints, and we have these challenges where we farm, where we operate. Some of the technologies, general classes that I'll talk about today, targeted applications, we'll go all the way back to the 1980s and talk a little bit about those into products that are available now. Certainly what GPS and rate control, droplet size control has done for us in spraying. And I'll talk a bit about new vehicles and UAVs. I know we have a lot on that later in the day. It's going to be very interesting to see the different perspectives of where we're going with effectively a new class of vehicle for delivering IPM. I want to go back to one of the first targeting sprays. And this is the use of ultrasonic sensors on orchard sprayers. Dave Miller, a few years ago, looking at spray drift, said, well, really, using LiDAR, he determined that most of the spray drift from orchards was coming from between the trees. And said the thing to do is simply turn off the spray between the trees. Very simple idea. When we looked at previous work that had been published doing accountability for where pesticide goes in orchards, we find that somewhere between 30 and 50% of the material applied ended up on the target. So we have tremendous waste, drift, but also ground deposit, inadvertent ground deposit. So the first sensors we have are very simple sensors. These are ultrasonic sensors mounted on the sprayer, looking outward, determining the presence of a target, and simply turning the spray on or off. That technology was developed in the 80s, it was commercialized, and it went almost nowhere. Few growers bought it, few people used it. Fast forward a few years later, we were having problems with OPs running off from dormant sprays in California, and we said, let's look at technologies that may reduce it. So we did studies first in some plums, then we went into walnuts. This is a close-up of the actual product, this time called a smart spray, first time that word was used. Ultrasonic sensors here, simple microprocessor controlling the spray output. We did a lot of work determining where the material went, spray savings. We then went into almonds, dormant applications, sampling spray deposit on the trees, ground deposit on the ground with the technology. Over 3 years, we collected data looking at the reduction in chemical application rate, and we found from about 15 to 40% reduction in rate simply by turning off, using the sensors to turn off the spray, and significant reductions in the ground deposit. So this is good, right? Reducing non-target effects, no effect on efficacy, and each spray load went further. So it met all 3 of those criteria. That wasn't enough for our regulators. They said, that's well and good, but what about the actual runoff? So they wanted one more study, a fourth year of a proven technology. So we said, all right, we'll go out and spray some prunes with the tree sensing sprayer. We measured spray savings again, ground deposit, and we actually collected runoff from the orchard and measured diazinon, which we had applied in that runoff. And we found, again, very significant savings. 40% reduction in the amount of spray, ground deposit by about 50%, and about 40% reduction in diazinon. And finally now, about 15 years after the technology was developed, about 4 years of research, this was approved by the state, it was implemented, and it now is a technology in which growers can get EQIP funds for buying the technology. So here's a technology, very simple, very sensor, but it took a long time to get implementation, and it took field studies. Now that work is actually continuing. At Ohio State, they're moving from simple ultrasonic sensors to more LiDAR-based sensing to get more information about the canopy, to do even better targeting of the materials. So here's a 20 or 25-year kind of longitudinal work on effectively one of the first sensor-directed sprays. As we continue looking at targeted delivery and focusing the application, using sensors, using mechanical actuators to improve that, the next place we looked was at lettuce and foliar application in the lettuce. Lettuce grows very quickly. The target is changing with almost every application that goes out. And in many cases, we found about 60% of the applications go out when only 6 to 8% of the land area is covered with target. So very inefficient application. So working with Dave Slaughter, we were doing the actuation. David was doing the sensing. This was one of the first video-guided cultivators or sprayers. Simply kept the toolbar guided on the row. That was a simple sensor implementation. We then created a spray nozzle and a system by which we could adjust the width on the fly of the spray pattern. Again, closely targeting that spray using the sensors. We went out, actually deployed this 12-row system in lettuce, went out and sprayed, and we found 60 to 80% reduction in the amount of material that we needed while maintaining same deposit on the crop. We reduced about a 90% reduction in soil deposition, a material that should be on the foliage. And we also found significant reduction in spray drift, not only due to reducing the rate, but also being able to bring the nozzle closer toward the target. So this was a very significant finding for us. Then as GPS was being developed, especially RTK GPS, this became a supplement to the video guidance. And now we see precision cultivators in which a combination of proximal sensing, that we'll hear more about today, and GPS, RTK GPS guidance, now very common in the Salinas Valley. Going one step further, looking a bit at work that, again, where David and I collaborated, was looking at distinguishing target weeds from non-target weeds or the crop. And the idea here is that we would come in and remove these very competitive weeds and possibly eliminate the need or the extent at which hand hoeing needed to be done. So remember our 3 aspects of pest control implementation. We're efficacious by removing those weeds. We're going to be more productive by removing a hand crew. and the non-target effects are reduced. So being able to distinguish our target and deliver a payload to that target, again, is part of this program, the theme of most things that we're doing. Dave developed the term leaf-specific agriculture. And the idea is that as we are better with what is now being called our proximal sensing, we certainly have more information in real time in the work environment. But quite often, the limiting factor becomes, what do we do with that decision? How do we target that weed? So we did a lot of work looking at first determining the target, distinguishing it spatially, and then delivering that payload, spraying the weed. Well, how are we going to spray this? Well, this is the level of precision that we need, certainly to remove these weeds at a very competitive time with a crop. We had to develop a specialized sprayer. We've never needed to spray at this level of spatial resolution, and this is only going to increase. The spatial resolution of agriculture, the trend is significantly toward a tighter resolution. Our information is at smaller and smaller scales. But what are we going to do with it? So looking at our sprayer, we simply don't have nozzles anymore. We have hypodermic tubes, and we have needles that are microdosing on the target plants. This is a close-up of one of our first systems, and it literally is hypodermic needles from which we're emitting jets with a spray times in the range of milliseconds. Not quite at microseconds yet. We're working on that, but we're at milliseconds here. Then the question becomes, okay, we can position our nozzle, our micro nozzle, close to the target. We can begin to release the material, but what happens to the material as it goes out? We're still delivering a payload, and we're getting closer and closer to our non-target area. Our crop is right next to our weed now. We're not concerned about kilometers of spray drift. We're concerned about centimeters or millimeters of spray drift now. One of the first things that we found, almost a very direct analogy to conventional spraying, is we need some adjuvants. These jets go out, and we can have very poor deposition, very poor penetration of the materials. So what do? Well, you go get a spreader sticker. That's what we do. Then we start getting a lot of splash because we've reduced the surface tension. Then we realize, oh, we've got to engineer the fluids now. We've got to engineer the payload and the payload delivery method. So by looking at combinations of water carrier and surfactants and polymers, we're able to get a very good spread without getting splash, inhibiting the splash. So then we started actually looking at documenting micro spray drift. Again, as our spatial resolution gets tighter, we need to understand what our spray drift curve looks like. This is water. This is water with a surfactant, a lot of splash. And this is water with our polymers or delivered in our oils. We effectively reduce the micro spray drift. So we're headed toward being very precise in our targeting so that we can take advantage of the sensing technologies that are out there. Now that work was done for a while, and simultaneously there was interest in thinning lettuce. Now this is not exactly a pest control operation, but hang on with me because I'll show you how it relates back to some of this work on microdosing. The issue is effectively coming in and removing or thinning lettuce after it's been direct seeded. And this has always been done with manual labor, in the same way that weeding has been done. Thinning has been done by hoeing crews. So with the improvement in being able to sense and target a spray, the idea was, well, let's effectively treat our non-desired crop plants as weeds and spray them. And so this would be a typical thinning operation on a bed of lettuce. These plants have been sprayed. They, of course, die from the application, and these plants will remain. So it's an automatic thinner. The interesting thing that's happened, and this is in the past 18 months, is we now have about 4 vendors. The the amount of venture capital coming out of the Bay Area, San Francisco Bay Area, Silicon Valley, is now going into agriculture. And this is enabling a number of companies to actually bring vision, guidance, and precision spray technology to the market. One of the most commonly known in California is Blue River Technologies. And effectively what they're doing is there's a vision system, much like the early work at UC Davis, and there's precision spray systems in here doing the thinning. So we're seeing now technology, again, where we had a 10 or 15-year time to market. And when it did come to market, it came to market very quickly with a number of competitors out, all operating in the valley and offering a service, if not a machine, to the industry. Going from the thinning, we now see work into adapting those machines for the weed removal. And the basic core of those machines will be very similar, and what will change is the distinguishing between crop and weed, and also how that weed will be removed. We're also seeing a number of mechanical systems, but again, the spatial resolution for mechanically removing weeds very close to target plants is very challenging. Remember back to about my third slide, the productivity. We can't go at a half mile per hour. However, the ability to work 24 hours a day, particularly with self-guided vehicles, is going to be a factor that allows us to maybe have slow technologies, but still have our overall productivity, our acres per day, acres per hour, quite high. So there's a lot of calculations, a lot of considerations that go into bringing these technologies actually into use. Looking now at environmental concerns, and again, our ability to sense and also manipulate our payload delivery. In this case, something very simple as changing our spray droplet size has a tremendous, is now finding a tremendous market in IPM, primarily in spraying. Many of the sprayers now that go out, self-propelled sprayers, these are $250,000, $300,000 machines. They all have guidance, they all have electronic rate control, and increasingly they have things such as weather stations installed on them. So one of the projects that we did a few years ago that's now very commercialized is the ability to manipulate the spray droplet size as the machine is moving across the field. And this is useful particularly when we tie it with our GPS sensing of our location and our onboard weather sensing. We effectively have all the information we need to mitigate spray drift. Where are we? What's the sensitive area? And what's the weather doing? We have this information on board. So again, how are we going to use this? What's our actuator? So we've done some work demonstrating spraying a field. This is actually at Davis. This is a residential area. This is a field to be sprayed, which we've mapped. This information is on board the sprayer. From our weather system that we have on the sprayer, we can actually track the location of the sprayer, the wind direction in decimal degrees, effectively the compass, and the wind speed. So in a field that we're going to spray, most of our wind here is from the southwest. It's from this direction. And our wind speeds are higher at the north end of the field. And this is just due to some local geography. So what we actually do is we mitigate the spray drift in real time as we spray. This is the field track of the sprayer. It goes up, makes one pass, and comes back. And we effectively change the droplet size as we were spraying without affecting the spray rate. And these were water-sensitive cards that we put down in the field. And this is our actual spray pressure on the boom. Higher pressure when we're away from a sensitive area and in low wind speeds, lower pressure and larger droplets when we have a drift concern. Not only can we do this in real time, we of course can report this to the operator and also the operator's supervisor. The last topic I want to touch on today is the use of new vehicles for our spray delivery. And we've been working quite a bit with UAVs, in this case, a small by some scales, helicopter, yet a large helicopter in the UAV world. And we've been focused on a lot of regulatory effort to get the approvals to do this. We first were told that dropping of objects from UAVs was prohibited. I said, no, we're just going to spray. And FAA said, Professor, let me explain to you. You're dropping objects. You're dropping spray droplets. They said, but if you do a safety analysis, maybe we'll let you do it. So we conducted a safety analysis, and they said, sure, you can go out and spray water. So we had a couple of operational areas in California. That was fun for about a year. We said, we really want to kill insects. We want to treat. We want to spray active ingredient. And so we applied again to actually spray, do chemical applications. And we actually had to comply with Part 137, which is the aviation rules that apply to crop dusters. So we're a crop duster now. And we can spray in some nut growing areas and some grape areas in California. This is the aircraft that we're deploying. It's been used for about 20 years, or some variant of it, in rice in Japan. It's a 200-pound aircraft. It's effectively a 250cc engine. So this is a substantial aircraft when it goes up. We can take up about 4 gallons of liquid, and it has a fairly conventional spray system on it. It's not autonomously operated yet. That's not approved. So this is operated with a controller. There's a pilot, an operator, with joysticks flying it. We focused on specialty crops. And the reason we focused is the areas are very challenging to spray, high value, lots of applications. Some of our grape growers spray every week. So there's a lot of opportunity to go out and spray. This is some of our test areas. This is one of our vineyards where we're operating. This is challenging to a ground vehicle because of the slope, because of the small rows and the turns. It's also challenging, almost unfeasible for a manned aircraft to spray because of the shape, because of the obstructions. So an unmanned aircraft is almost a niche application for this. And so this is where we've been focused. Remember, our first year, we could not spray chemical. We sprayed water. So we used water-sensitive paper to assess our spray deposition. Those of you that have worked with it know that it starts out yellow, you spray and you get a record of your spray droplets. It turns blue. This can then be scanned in, and we can assess visually or optically the deposition. We also wanted to, again, look at productivity. So we measured the times for all the operations, filling, ferrying, and spraying as we worked. In our first years, we couldn't modify due to regulations of the aircraft. So the only way we could change our application rate was to adjust our swath width and the number of passes that we made. And what we found was it's a lot like aerial application. We could achieve aerial application rates of about 1 to 3. Now we can get up to about 5 gallons per acre. Very consistent with manned application rates. How fast was it? It's fast. We got a lot done. We could work from about 3 to 7 acres per hour. An equivalent ground application in some of these vineyards is an acre per hour or less. So very fast productivity with this application. We then expanded to looking at active ingredients this year once we had the approval. One of the first things we wanted to do was spray weeds, look at targeted weed control from the aircraft. We're in the middle of a drought. Normally, this field would be completely green and you'd need a machete. So we had to plant some weeds last year. It was so dry. So we did what most folks do when you need weeds. We went to Home Depot and we bought some turf that we established. And we got it laid out in the field. There's some blooming almonds upwind here. We did a couple of passes, looking at mostly visual assessment, just understanding our swath width and how well the application could work. And lo and behold, the turf did die. This is the control, and this is the treated. And what was really interesting was how precise the edge of the pattern was. Very little displacement of visually, as we saw, very little displacement of the spray pattern. We then went out spraying more season-long disease control in vineyards this past year. This was from about April through July. Looking at mildew control, we had very low pressure, so we really didn't see differences in our treatments, but we had absolutely no problems with deploying the aircraft season-long. We followed a grower chemical regime, and the aircraft and the applications went out just fine. We did conduct a tracer study looking at deposition, comparing to ground rigs after harvest. We had canopy. We applied micronutrient tracers by ground and also by a couple of aircraft configurations, pulled the samples, analyzed, and we found effectively that all our treatments were giving us very similar deposition. So we can now go out at 7 acres per hour with the unmanned aircraft and achieve very similar deposition of chemical as a 100-gallon per acre, 50 to 100-gallon per acre ground application. There's some topics, though, UAV spraying, we'll hear more about this today. I want to make a couple of quick comments. We do have conflicts over airspace. The place where we're operating these UAVs is right in the middle of where commercial crop dusters and ag applicators operate. So the potential for conflict there is significant. So where most of the UAV world is unconcerned because they're low, they're in uncongested areas, the thought is we're out of commercial airspace. Not so for agriculture. We're right where the manned aircraft are. And we have questions about what are the labels going to allow us to do. We all know that when we look at the label, we find fairly specific instructions, especially with aerial application. And for some registrants, this may be their label solution to UAVs. Problem goes away. Liability, uncertainty, say we don't want to deal with it. This is not what we want to see, or at least not without a great deal of thought before that decision is made. But it is a solution to the problem of what to do about UAVs and spraying. We're increasing our work on increasing the spatial resolution from UAV spraying. We've developed a sprayer, very targeted sprayer, small payload. It's actually powered off a CO2 cartridge. It takes no electricity from the aircraft. Very light system. Radio control for the spraying. Also, there's a camera here. So effectively, this becomes our spray operator. He's wearing goggles. He can be miles away, not unlike shooting in caves in Afghanistan from an Air Force base in Nevada. This is the type of technology we can bring in using the UAVs. He's looking through the goggles, trying not to get motion sick, and looking for spray targets. We tested this system for safety. We didn't put it on a UAV first time out. So it's mounted on a pickup truck, and our spray operator was aiming for orange cones. Did a pretty good job. Got about 83% of them. So this is how we can deal with operator exposure with UAVs. Where would we use something like this? How about this? Controlling invasive weed species. This is how it's done in some places. You rappel down with a backpack sprayer. So, yep, this guy is a sprayer. This is your handgun guy. Some of the weed removals cost about $700 per weed in this, controlling these invasive species in natural areas. This is a place where deploying a UAV has a lot of advantages. So again, what we've seen over many years of research and development with new technology and also bringing it to market, it takes a while. We have to address all three aspects of pest operations, efficacy, non-target effects, and productivity. But there's some very exciting technologies coming along. And again, thank you, Steve, for this opportunity to come and meet this group and share what we're doing.